A scientist just said something that should stop you cold. If you flew a spacecraft directly toward the center of the Milky Way, toward the object we have spent decades calling a supermassive black hole, you would not be torn apart. You would not cross an event horizon and disappear from the universe forever. You would pass straight through, peacefully, and come out the other side. Those are not the words of a science fiction writer. They are the words of Carlos Argels, astrophysicist at the National University of La Plata in Argentina, published in a peer-reviewed journal in February 2026. His team's research proposes something that challenges one of the most iconic images in the history of science. The photograph of what we all believe was our galaxy's central black hole. The object we called Sagittarius A star. The 4 million solar mass monster that every star in the Milky Way orbits. It may not be a black hole at all. It may be something we have never directly detected. Something that makes up 85% of all matter in the universe. Something we have been searching for since the 1930s without ever finding it. Dark matter. And if this theory is correct, it does not just rewrite the story of our galaxy's center. It solves one of the deepest unsolved problems in all of physics simultaneously. The story of Sagittarius A star begins in 1932 when a radio engineer named Karl Jansky detected an unusual signal coming from the direction of the Sagittarius constellation. Nobody understood what it was. Black holes were still considered mathematical curiosities, theoretical objects that the equations of general relativity permitted, but that most physicists doubted actually existed in nature. It took until 1974 before the signal was identified as a single compact object at the galactic center. Astronomers Bruce Ballack and Robert Brown pinpointed it. Brown named it Sagittarius A star, the asterisk denoting its unusual radio brightness. Then in the 1990s, something remarkable happened. Improved telescopes allowed astronomers to track individual stars near the galactic center, stars moving at speeds that made no sense. These stars, called S-stars, were racing around an apparently empty region of space at extraordinary velocities. One of them, designated S2, completes a full orbit in just under 16 years. For comparison, our Sun takes more than 200 million years to complete one orbit of the galaxy. The only explanation that fit was an object of approximately 4.3 million solar masses packed into a region small enough to fit within the orbit of Venus. The researchers who proved this, Reinhard Genzel at the Max Planck Institute and Andrea Ghez at UCLA, won the Nobel Prize in Physics in 2020. Then in 2022, the Event Horizon Telescope released the most anticipated image in the history of astronomy. A photograph of what appeared to be the shadow of a black hole at the center of our galaxy. A dark circle surrounded by a bright, glowing ring of superheated matter. The case seemed closed. Sagittarius A star was a supermassive black hole. The evidence was overwhelming, except for one carefully chosen word in the Nobel Prize citation that almost nobody noticed. The official citation reads, "For the discovery of a supermassive compact object at the center of our galaxy." Not black hole, compact object. Because despite everything we had observed, the orbiting stars, the Event Horizon Telescope image, the Nobel Prize itself, the true nature of Sagittarius A star has never actually been proven. Scientists have never directly detected a black hole. They cannot. Black holes do not emit light. Their existence is always inferred from their effects on surrounding matter. And that inference, however compelling, leaves a door open. A door that a team of researchers in Argentina walked through in February 2026. Valentina Crespi at the Institute of Astrophysics La Plata had a question that sounds almost absurd at first. What if the object at the center of the Milky Way is not a black hole, but a dense ball of dark matter? To test this, her team built a mathematical model of what such an object would look like if it existed, a core of fermionic dark matter, and then compared its predictions to real observational data, specifically the orbital paths of S2 and 5 known G objects. Dust-shrouded bodies near the galactic center that distort visibly as they pass close to Sagittarius A star, stretched and pulled by the intense gravitational field. The results were published in the monthly notices of the Royal Astronomical Society in February 2026, and they were remarkable. A dense core of fermionic dark matter reproduced the observed orbits of S2 and the G objects with less than 1% difference from the black hole model. The gravitational effects were statistically indistinguishable. You cannot tell the difference between a dark matter core and a black hole using the current observational data. But the model went further than just matching the S-star orbits. A 2024 study by the same group had already demonstrated that when an accretion disk of superheated matter surrounds a fermionic dark matter core, it produces a shadow-like feature strikingly similar to the one the Event Horizon Telescope photographed in 2022. The dark circle surrounded by a bright ring, the image the world celebrated as proof of a black hole, could be produced by a dense dark matter core bending light with the same intensity. As Crespi herself stated, the dense dark matter core can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. The photograph we thought proved the existence of our galaxy's black hole may be consistent with something else entirely. To understand why this theory is so significant, you need to understand the problem it is trying to solve. Dark matter is the single most abundant form of matter in the universe. It makes up approximately 85% of all matter that exists, and yet nobody has ever directly detected a single particle of it. We know it exists only because of what it does, the gravitational effects it produces on the things we can see. It was first proposed in the 1930s when astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving far too fast to be held together by the gravity of their visible matter alone. Something invisible was adding mass to the system. He called it dark matter. Later observations confirmed this on galactic scales. Stars in the outer regions of galaxies orbit at speeds that cannot be explained by visible matter alone. And the Milky Way itself appears to be surrounded by a vast diffuse sphere of dark matter extending far beyond its visible disk of stars, called a dark matter halo. We know dark matter exists. We have known for nearly a century. What we do not know is what it is made of. It does not emit light. It does not absorb light. It does not interact electromagnetically with ordinary matter in any detectable way. Every experiment designed to catch a dark matter particle directly has come up empty. This is where the La Plata team's proposal becomes genuinely extraordinary. They propose that dark matter is made of particles called dark fermions. Fermions are a class of subatomic particles. Electrons and quarks are fermions, and they obey a fundamental rule of quantum mechanics called the Pauli exclusion principle. This rule states that no two identical fermions can occupy exactly the same quantum state at the same time. In practical terms, this means fermions resist being compressed together. They push back. They cannot be infinitely squeezed into a singularity. Dark fermions would behave the same way, but they would only interact with the rest of the universe gravitationally, making them completely invisible to our instruments. Under the right conditions, dark fermions could clump together, build up enormous internal pressure from the Pauli exclusion principle, and form an ultra-dense stable object, one massive enough to mimic the gravitational pull of a supermassive black hole, without ever forming an event horizon or a singularity. And here is the detail that makes this theory unlike any other alternative to the black hole model. Dark fermions do not just form a dense core. They naturally extend outward from that core, gradually becoming less dense as they spread through the galaxy and beyond, forming exactly the kind of diffuse spherical halo that dark matter models predict surrounds the Milky Way. The compact core at the galactic center and the dark matter halo surrounding the entire galaxy would not be two separate objects. They would be two parts of the same continuous structure, the same substance, at different densities, unified into one physical system stretching from the very heart of the galaxy to its outermost edges. As the team describes it, we are not just replacing the black hole with a dark object. We are proposing that the supermassive central object and the galaxy's dark matter halo are two manifestations of the same continuous substance. No other theory of Sagittarius A star does this. Every other model treats the compact central object and the dark matter halo as entirely separate things. This is the only theory that unifies them. The S-star orbits and the Event Horizon Telescope shadow are not the only observations this model needs to explain, and it explains them all. ESA's Gaia mission has been mapping the positions and motions of 1 billion stars across the Milky Way with extraordinary precision. In 2022, Gaia revealed something completely unexpected at the outer edges of the galaxy. a slowdown in the rotation of its outer spiral arms called Keplerian decline. Stars at the galaxy's outer edges were slowing down in a way that most dark matter models could not reproduce. But fermionic dark matter, because of the Pauli exclusion principle, naturally forms a dark matter halo with a sharper, more clearly defined outer boundary than other dark matter candidates. This sharper boundary would produce exactly the kind of rotational slowdown Gaia detected. The same model that explains the object at the galactic center also explains the rotation of the galaxy's outermost stars. One unified substance, one continuous structure, two observations that previously required separate explanations, now potentially accounted for by a single theory. And there is one more piece that connects this to something even larger. The James Webb Space Telescope has been finding extremely massive compact objects in the centers of galaxies, so young that they should not have had time to form supermassive black holes. These objects, nicknamed little red dots by astronomers, have mass in the hundreds of millions or even billions of solar masses, existing when the universe was less than 1 billion years old. Fermionic dark matter cores could have formed far earlier in cosmic history than black holes, because they do not need stars to collapse and merge. In the dense conditions of the early universe, dark fermions could have clumped together and formed compact cores without any stellar starting point. The little red dots that have been puzzling astronomers since Webb began operating may be exactly what this model predicts: dark matter cores in young galaxies, not black holes at all. Here is what this theory is and what it is not. It is not proven. The consensus among astronomers still holds that Sagittarius A star is almost certainly a supermassive black hole. The La Plata team themselves are clear about this. Their work does not prove the black hole model wrong. What it proves is that the fermionic dark matter model cannot be ruled out by current data. The two models are observationally indistinguishable with the instruments we currently have. What distinguishes them, and what could settle this question definitively, is something called a photon ring. Around a true black hole, the intense gravity near the event horizon forces photons to spiral multiple times before being swallowed. This phenomenon produces a distinctive pattern in the light surrounding the black hole that can in theory be detected. A dark matter core has no event horizon. Photons near it are bent by gravity, but ultimately escape rather than being trapped in endless loops. No photon ring would form. NASA's Black Hole Explorer mission aims to launch a space-based radio telescope that, combined with the next-generation Event Horizon Telescope, would create a virtual instrument larger than Earth itself, sensitive enough to potentially detect or rule out photon rings around Sagittarius A star. But this could take decades. In the meantime, the gravity interferometer in Chile is continuously measuring subtle changes in S2's orbital path with each loop around the galactic center. And direct detection experiments like the NEON experiment in South Korea are hunting for the minute energy traces that would be produced if a dark fermion particle collided with an electron. We are looking for two things simultaneously: a photon ring that would confirm a black hole and a particle signal that would confirm dark matter. Finding either one would answer one of the deepest questions in modern physics. Finding neither would leave us exactly where we are now, staring at the heart of our own galaxy, unable to say with certainty what is actually there. Think about what that means. We have photographed it. We have tracked stars orbiting it at 10% the speed of light. We have won Nobel Prizes studying it. We have published the most celebrated image in the history of astronomy. And we still do not know what it is. The center of our own galaxy, 27,000 light-years away, remains one of the greatest unsolved mysteries in science. And the answer, when it comes, will change our understanding of not just one thing but two: what anchors our galaxy, and what most of the universe is actually made of.